Hey folks, join me for Networking 101. There might be a quiz later. You know, we use fiber optics nearly every single day, right? Either it's from the data that's being transferred across it, or we're actually using it to really cover those really, really long distances. But when it comes right down to it, what's really going on underneath this little shielding here? What is the real deal that's happening in fiber optics? And does size really matter when it comes to it? You know, you may be surprised. Fiber optics, or at least the principle for light transfer, happened around the 1840s with a guy named Daniel Colladon. What Daniel did is he was shining lights down water pipes. I guess he didn't have much else better to do. And he noticed that the light would kind of follow the water. And he said, huh, that's pretty groovy. I wonder if I can do something with that. And then it wasn't until the 1960s when Charles Cowell came up with an idea of actually using really pure glass to transfer this, that it really became a reality, and Corning, you know, started developing fiber optics, and then it really took off from that point. But let's go ahead and focus on really what happens in this little small piece of glass, if you will. Now, it really honestly is glass. This is very pure, very extruded glass that they're actually extracting out to transfer this light across. Realistically, you're looking at something that's about 10 to 100 times smaller than the diameter of a human hair. So, man, you're really got some really, really small, you know, glass in here. As a matter of fact, probably one of the worst cuts you'll ever get in your life is if you have to mess with terminating these things and get a piece of that glass in your finger. It just doesn't come out, and man, is it painful. Holy smoke. So anyway, let's go ahead and talk about what we're looking at when we're looking at how this fiber transfers. So if you look at the tech board, this is a piece of fiber here, and what we're looking at basically is like a glass sandwich, if you will. But you have to understand that this is a cylinder. It's round, and so there's a piece going through this, right? What we have here, this outside piece of this fiber is called the cladding. I'll just abbreviate it CL. This inner piece is what's called the core. Now, when you go to buy fiber optics, you're going to notice that it's actually rated with two numbers. It'll say 125 slant 62.5. And basically what that's saying is that this cladding is 125, the core is 62.5 to carry your light across. Now, that's pretty good for the physical characteristics of fiber optics, and the same goes with you know, single mode, the smaller, the 9 nanometer stuff. But really, how do we get this to work? Well, we got two different modes that this can really transfer down. The 62.5 is what we call multi-mode fiber, or MM. The smaller diameter stuff is what we call single mode fiber, and this is where it gets a little confusing for some folks to kind of get it. So when you're looking at single mode fiber is a lot smaller. It's 18.9. And typically you'll notice a pattern, right? It's usually double the size. And this is what's inside. This doesn't count the jacket on the outside of it. There is a measurement for that, but I don't remember what it is. It doesn't really matter. The important part is to know the core and the cladding is really how we're transferring this data. Now, as we're shooting light down this, what we're trying to do is that on multi-mode fiber, we have what's an LED light, right? We all use LEDs all the time. Really cool, really efficient way to light up different, you know, areas and stuff. Really cheap too, usually. We use infrared LEDs to blink on and off and send this signal down. And at the end, we've got some photocells. In this example, usually it's like a photodiode that's detecting this infrared light as it comes down. Now, here's the trick. As you're sending this down, basically it's the angle of this LED or the lens that's going to take this light, it's going to shoot that data in, so this is a 1. It's going to shoot that 1 in, and it's going to bounce off of this cladding. This cladding is highly reflective, and so anything that comes into it will bounce it, and it'll come down again, and boom, it'll bounce off that cladding, it'll bounce, and it'll keep bouncing up and down this line until it travels down. And that's really the essence of how fiber optics really works, is that I've got a highly reflective piece and another piece that the core that allows this light to transfer up and down it. But for this light to transfer, it has to be called what's in phase. Now, as these waves move, they move actually what we call wavelengths, right? And if you remember, we've talked about wavelengths before on Networking 101, on TechWise TV and stuff like that. Wavelengths, you'll see them a lot the more you start dealing with fiber. They're represented by the signal lambda, or the symbol lambda, and it's basically the speed of light which c is always the speed of light, right? If you're talking like EMC squared, that type of stuff. C is the constant for the speed of light in a vacuum. That represents about 186,000 miles per second in light. Now, if somebody says, oh man, my fiber optic is traveling at the speed of light, not really. It's really it's fast, certainly, but this is speed of light in a vacuum, optimal speed, if you will. That's the marketing speed. F is the frequency of that form, and then our other measurement is N, our reflectivity index that we have in our fiber itself to actually say what is going to be in phase on this, to go down this fiber. Multi-mode is indicating that it can transfer fiber in a lot of different modes. We can have a lot of different phases, if you will, and that light still will move down this line. Waveforms are what we call wave fronts they'll be standing waves. They'll kind of be bouncing up and down, and they'll be out of phase, and they won't be able to transfer down that line. Now, multimode does support quite a few different wave fronts, if you will, so you can transfer a whole lot more than what we could in anything else. But for the most part, that's how that moves. In single mode fiber, a little more tricky. You still do have the same movement here, but our mode that we support is a single mode. It's only going to allow one type of mode for that line to come down. It's going to reject a lot more. And why? It's a lot smaller, right? The core is a lot smaller in here, so it doesn't have much forgiveness. And to shoot this light down here, we're using a small laser, an infrared laser, to shoot that off. We got another photocell here that's picking up that energy as it's being transferred and can catch that. Now, a couple really cool things here. If you're shooting this down a very long distance, this fiber, and we're going to like shoot this like back in, I think it was like 1997, England laid one of the longest fibers. It went from England to Tokyo, went all the way around the world. They call it the flag line, right? Fiber optic line around the globe. And it was the longest, continuous strand of fiber, if you will, that was laid all the way around the world. And what they did is that they figured out a way to what you call dope this fiber, where you can put like acceleration zones in here, like you're playing like a really cool racing game, like Mario Kart. You got the little arrows there, and when you hit over them, you actually go a little bit faster. Well, that's kind of how this works in long distance fiber as well. Is that you have these doping spots in here, and then we have a laser that pumps. And literally that's a term, that pumps these spots, and it will regenerate that signal almost like a switch does, right? And it will send it down, and so you can really send this a very, very long distance, and it works pretty darn cool, right? So that's how that takes off. A couple pieces here that I think are really important to mention. Now, we talked about multimode and how it will pretty much accept just about anything. Multimode is really the really let's give peace a chance kind of fiber, right? I mean, it accepts anything. It's really cool. You can shoot all kinds of modes down there. It's going to pretty much work. There are a couple different sizes that are popular. In the U.S., you're really looking at about 125 6.25 or 62.5. In Europe, typically you're going to see 100 and 150 are the more common type of standards here that you'll see. Now, you'll see some of this in the U.S. as well, but for the most part, I see more 150 over on the European side. Now, real quickly, what you should know is that when you look at that number, you can tell that that core is squeezed down just a little bit, right? So that means that we should get a little bit better distance, and that's true. Just like a fire hose, if I turn that nozzle to the little pencil stream, I can shoot it a lot farther than what I can as the fan stream, and that's what we're looking. The smaller that core gets, the better our distance is on here. And since it's multi-mode, it's very forgiving, and it ages really, really well. So if I have this on and it's been out there for a few years, it's still going to perform just like it's supposed to, because multi-mode is very forgiving. Single mode, on the other hand, is not forgiving. It only is single mode type of fiber. So the problem that a lot of people run into when they're setting up single mode fiber is that they'll have to bridge a long distance, a few kilometers, with their single mode fiber, if you will. And that's great to have that trunk line laid. But then when they plug in their switch or their router, what they'll connect that with is a standard multi-mode patch cord. And this is very common. You'll see people do this all the time. I've done it plenty of times. And what you have is you have an issue that's called modal dispersion when that happens. Because now I'm saying that I've got this long 62.5 core in here, and I'm reducing it down to a 9 micron core to send that light across, and that causes all kinds of rejection errors at this end, and can cause some bandwidth problems and things of that nature. So if you're going to connect up to a single mode line, probably one of the best things you can do is get an MD cable, or what some people call a launch cable. And sometimes that is still single mode because it's cheaper and it's a lot more durable to build that on your network. But what it has is, if you split this jacket here and you look at the optical lens on the inside, what you're looking at is, as your fiber is coming down, it kind of goes to a kind of a conical point, and it starts to shape that signal to make it ready to attach to a single mode line to decrease that modal dispersion. So now, as signals are going out of phase, then they start bouncing up and down. The ones that are out of phase we want to reject, and they won't go down. Only the good signals that are in phase will pass straight through this line and get out. Fiber is really cool, man. It's been around forever. If you really want a really cool kind of science experiment to do, you could take like a regular soft drink bottle and wrap some aluminum foil around it, and then fill it full of water, and get a really bright flashlight and shine in the bottom of it. Turn your lights off wherever you're going to be, like in the bathroom, you know, make it kind of scary dark. Woo! But then take a really bright flashlight and shine through it, and then start to pour that water out. And what you'll see is, as the water's coming out, the light's going to follow it down a little bit because it's bouncing up and down. It's using that water as a conduit, and you'll see it kind of arc just a little bit. And then and photons are very, very light, so don't expect to see like a really cool kind of light thing. But you will see a nice arc of the light coming out, and it kind of shows you what Daniel Colledon saw, and he said, "Hey, this is pretty cool. I wonder if I can use this one day." And then, of course, 120 years later, we found out we could use it. Fiber optics is cool, and we use it every day.